All right, we're going to look at triangles. Now, there's a historical reason for this. Most of mathematics came from geometry initially. The original ideas outside of counting that built a lot of what we needed to do came from construction. And so the main object that was studied was the idea of a right triangle. And the reason this was studied, so we'll make a right triangle. These angles form a right angle, which is 90 degrees. And this really lays underneath a lot of the concepts of what we do with number, because this helped builders. Like if you want a perfectly straight building, it's at a right angle to the ground. And so the right triangle was in early buildings. The Egyptians had an idea of what would become the Pythagorean theorem. They had ropes with knots on them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they'd have 12 knots on a rope, and they would stretch it so that there were 3, 4, and 5 knots, and they could guarantee that was a right triangle. And we're going to see why that's true and why triangles pop up a lot in mathematics. And there's a lot of relationships from a triangle that we then borrow on numbers. Later on, we'll see that we graph things, where we can talk about the x value and the y value on a grid made at that the two values are at right angles to each other. And that gives us a lot of little triangles in here. And so this concept underlies a lot of how we historically learned to do patterns with numbers. But one of the things that's going to come out of this is if we look at a triangle, a right triangle, if we have a square or any rectangle, the diagonals form the triangles out of it. And so one of the numerical concepts we have to get is what is the square root of a number. And so these two concepts of squares, where we have these right angles, and the triangles that get formed from them, we're going to have to explore mathematically. So the idea is if I have some square root equal to something, well, if I square that something, I get a number back. And that's going to be the thing that that we use to define this. Now, a weird thing about square roots is the thing inside this a part can't be less than 0. And let's look at why. If this thing squared gives us the original number, that means that there's something that times itself equals a. So if I have -1 times -1, well, a negative times a negative is a positive. And I have 1 times 1, it's a positive. In fact, anything squared multiplied by itself will always be a positive number. So square roots only work for positive numbers or 0. So the square root of 0 is going to be 0. So let's look at some square roots. The square root of 81. So I need some number times itself equals 81. Well, for us, it's 9, because 9 times 9 equals 81. Also, if I do 1 over 25, that's the same as the square root of the top and the square root of the bottom. Well, 1 times 1 is 1. And what number times itself is 25? That's 5. So if I have a larger fraction, 9 over 64, I can look at the square root of the top and the square root of the bottom. So I have to think of some number times itself equals 9. It's going to be 3. And some number times itself equals 64. That's 8. What I like to do when working on square roots is I kind of want to think about squaring numbers. So if I take 1 and I square it, so right now I'm just going to call this my x values, and this my x squared values. 1 times 1 is 1. If I take 2, 2 times 2 is 4. If I take 3, 3 times 3 is 9. If I take 4, 4 times 4 is 16. If I take 5, 5 times 5 is 25. If I take 6, 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. And 12 times 12 is 144. And so I can use this table backwards. If I'm looking for 81, well, here's 81 in my squares. So the square root is 9. And so that's how I kind of think of this. Now, other numbers, notice there's gaps in here where I don't have perfect squares. And so if we use our calculator as a tool, we'll come down to here, I can take 58, whoops, let me actually write in 58. And on my calculator, I should have a square root key. And so the square root of 58 is some number that has a lot of decimal places. I'm just going to round to 3 decimal places for right now. Is 7.61. Notice 7 times 7 is 49, and 8 times 8 is 64. So 58 has to be somewhere in between these. And it is. So we can look at some other square roots. The square root of 13. Well, before I put it on the calculator, I'll look. 13 is between 9 and 16. So my answer is going to be somewhere between 3 and 4. So if I type it on my calculator, I get 3.606. And the square root of 89, well, it's bigger than 9, but less than 10. And I type it on the calculator, and I get 9.434. And so that's the square root. Now, why the square root is important is that Pythagoras, the person that came up with the word philosophy, found a relationship on right triangles. That's always true, no matter the type of triangle, as long as it has one right angle. And so what we're going to do is we're going to use the right angle, the squared side of it, to define the other parts of the triangle. So the thing opposite the right angle is called the hypotenuse. And then in the two parts that make the right angle are called the legs. Now these legs can be different sizes, so we're going to call this one A, this one B. The hypotenuse will usually give the letter C. And what Pythagoras found was that A squared plus B squared equals C squared. Always. So the square of the legs equals the square of the hypotenuse. So remember I said the Egyptians had a rope so that they could put 3, 4, and 5. So let's verify that. 3 squared plus 4 squared equals 5 squared. Well, 5 squared is 25. 3 squared is 9, and 4 squared is 16. And 9 plus 16 is 25. And so this became a construction tool that you could make a right triangle with, as long as you knew what the size of the legs were. So let's look at an example here. So I have a 12-foot leg and a 16-foot leg. One of the things I could ask myself is, how far is it from here to here? We can think of this also as a distance, right? A straight line distance. So what I want to know is a squared plus b squared equals c squared. Well, I know a and b. So 16 squared plus 12 squared is equal to c squared. Well, 16 squared, run to my calculator, is 256. And 12 squared is 144. So I add these together, and I get 400. So c squared is 400. Well, if I take the square root of c squared, I have to take the square root of 400. And the square root of something squared is just c. So the square root kind of undoes the squaring. And the square root of 400, well, if I run to my calculator, is 20. So the length of this side is going to be 20. Let's look at another right triangle here. Clear my board. And so this is the right triangle. And I'm going to have a leg that is 48 meters and another leg that's 22 meters. So I want to know the length of my hypotenuse. So again, I'm going to look at a squared plus b squared equals c squared. So 22 squared plus 48 squared equals c squared. Again, I'm going to use my calculator. This is 484. And this is 2,304 equals c squared. Well, I add these together, and I get 2,788. And so now I take the square root of both sides. And so c is going to be the square root of this. I type this on my calculator. I get around 52.8. I'm going to have to put an approximate sign here because it's not exact. And so this hypotenuse, well, I didn't have decimals here, so I'll say this is 53 meters. Let's look at what happens if I know the hypotenuse but not one of the legs. So I know 3 yards and 9 yards. So if I say this is A and this is B, A squared plus B squared equals C squared. I know I have 3 squared plus B squared, because I don't know what it is, equals 9 squared. So 3 squared is 9, and 9 squared is 81. So I'm going to solve for b squared. So I'm going to subtract 9 from each side. And that gives me 72. So I take the square root of both sides. And b is going to be approximately, again, I'll run to my calculator, 8.485. And so if we round, this is like 8 yards. Right? It's kind of in the middle. But it is smaller than the hypotenuse. In fact, no leg can be as long as the hypotenuse. That's one of the little secrets that come out of this. let's look at some things we can do with these, and how triangle relationships help define a lot of the math we're doing. That you might not think you will ever need triangles. But again, because of a lot of the tools we use for mathematics came from measuring things, these hide behind some of the things we do. So we use triangles for something we can visualize, but later you'll see this pattern come up more and more often in other things we do. So it is one of those things where nature gave us a pattern. Well, when we can look at triangles, one of the things we want to figure out is, are they congruent? So congruent triangles have the same shape and the same size. So if I look at congruent triangles, and let's say A is equal to 6, C is equal to 11, and B is equal to 9, then this other triangle has to have the same, we'll call this, I'll give it a different letter, and let me go alphabetically. This side, D equals 6, E equals 9, and F equals 11. They have the exact same lengths. And that means they're going to end up having the exact same angles. So I'm going to use a little way of marking angles here. I'm going to use little half circles. And so these partial circles to mark the angles are going to be the same measurement. And so congruent is a way of saying that the triangles are equal. So to find triangles that are congruent, we only need to collect things that in threes. Triangles come in threes. So we can say that angle, side, angle. And notice how I'm positioning these. I have angle with a side in between the angles. So if I make a triangle here, and let me try to make a triangle here. If this angle, which we're going to measure, is 45 degrees, and this angle here is 35 degrees, and this side is 14 centimeters, then I can say this triangle is congruent if I have the same relationship. I have angle are the same. The side in between the angles are the same. Angle, side, angle. And so these are congruent because I've trapped the side in between the two angles. And so angle, side, angle is one way that we can find congruent triangles. The other way is if all three sides are equal. Side, side, side. And that's what we had up here. We had all three sides equal, so we know these triangles are congruent. Notice how I'm comparing three things in the triangle to make sure they are the same. And the other way we can get this is side, angle, side. So let me draw my triangle here. So this is, whoops, let me draw the other one. This is 23 feet, and this is 14 feet, and this is 23 feet, and this is 14 feet. If these angles are both the same, which in this case is 50 degrees and 50 degrees, these triangles are congruent. So I can trap an angle, side, angle. I can have all three sides the same, or I can do side, angle, side. And so we can find congruent triangles by matching up three components in these special forms. Two angles with the side in the middle, or two sides with the angle in the middle, or all three sides. And we'll explore triangle relationships more as we look at geometry.